can be done with Linux, especially if you have one of those Linux sys things that run Linux anyway. You can do some funky stuff with that. Next layer up is obviously layer 3. That is the whole IP thing. This is, routers, basic services, and that internet thing all talks IP. It's worth bearing in mind that while most of the time layer 3 runs across layer 2 and layer 2 is Ethernet, layer 2 in terms of the internet can be a bunch of different stuff. It's not uncommon for layer 2 on the internet to be ATM, MPLS, PPP, HDLC. It can be a lot of different protocols. So we aren't going to touch on any of those layer 2 protocols other than Ethernet. You're laughing at. And then we move on to the fourth layer, which is TCP, UDP, ICMP, ports, protocols used for basic network services. Pretty much anything you're going to use on a network will be using one of those protocols. And if it's not using that, it's probably not using IP, in which case we don't care about it. So that's kind of a general overview. Any questions so far before we delve further in? I don't know if that's good or bad. I'm going to assume it's good. Okay. Ethernet, otherwise known as 802.1, or it's actually 802.1, yeah, by the IEEE. Ethernet is basically a frame-based system. It learns. It's a learning system by design. It learns where systems live in terms of a switch network. You start out with basically a blank network. You send a broadcast saying, where is this IP address? And then it learns where it is. It learns the MAC address from that. And then it learns which MAC address goes with which port. Then it knows how to send the packets and the frames and stuff. So in some senses, Ethernet has some HA capabilities built in, because you can get a network device, unplug it from one switch port, plug it in another switch port, and everything just keeps working because it relearns where it is. A couple of different things you can do with Ethernet to make it HA. This really has nothing to do with Linux right now, but it's a pretty good precursor to the other stuff. You can use multiple links between two switches, bonding, ether channel, a couple of different names for it. Basically, what it will do is it will just do per frame load balancing over these two links. One goes down, it'll send it over the other one. So it's kind of useful if you want to do two separate paths. So say if you're going between two switches in a building, you want to take one link one way, one link another way, just in case somebody cuts through it, then you can do that. Obviously that increases your bandwidth, but it doesn't give you a whole lot of redundancy, because if the one switch fails, you're still screwed. Ethernet itself actually has a pretty good system called spanning tree that is really nice in terms of handling lots of switches on a network and figuring out the best way to route everything. Spanning tree is kind of like OSPF, but it's for layer 2. It will learn which switches are connected where. It'll figure out the cost of each path, all that kind of stuff. Originally, it was designed for detecting loops in networks. So if you got two switches and plugged them both into each other, you didn't get the whole broadcast storm like you normally would. It would say, oh, this switch is available on both ports. Let's turn one of these ports off, and then we avoid that routing loop. Now, one of the side effects of that is that you can get a giant switch network, plug it all in together, turn spanning tree on, let it figure out the topology of the network, and everything will just sort of figure out the best way. It'll use, say if you've got GigE and FastE, it will use the GigE links and preference, all that kind of stuff. Linux supports Ethernet about as well as anything else on the internet, apart from Microsoft. It has the capability of creating what is known as an Ethernet bridge, which is basically a switch. So if you have a Linux box with 4 network ports, you can essentially make a switch out of those ports using the bridge module. It's actually a really good system. It supports spanning tree natively, so you don't have to mess around with any user space junk. It's all in the kernel. And it's really simple to set up. Most Linux distros these days, like I know Fedora does, Red Hat, Debian, Mandrake, they let you set up bridges and stuff like that really easily within their configuration files. You don't have to go through and hack stuff by hand, which I'm sure some people will be disappointed. You can still hack it by hand if you want to, but you can obviously set it up so that at boot time it does spanning tree. Linux also supports Ethernet bonding using I think it's if nslave or something like that is the kernel, the command line tool for it. Basically, if you have two NICs in a box, it will withstand one NIC failing, but it won't, since they both have to go into the same switch, it won't cope with the switch failing. So you kind of have to weigh up, do I want extra bandwidth versus do I want extra redundancy? You can get gig Ethernet cards now pretty cheap, so is it really worth getting 2 gigabits per second versus actually having the thing up all of the time? Spanning tree is great simply because it's really, really quick at rebuilding the topology on the network. Essentially, the way it works is that all the switches talk to each other using spanning tree. They figure out which one is what they call the root bridge, based upon a cost that you can give each bridge, and a priority for a cost for the port and a priority for the bridge. So you would say if you have, say, core gigabit switches, then they would have a higher priority than any sort of fast Ethernet switches. All these switches will learn from each other, how to get to different networks. They will learn the topology of the network in terms of, if I want to go here, I've got these 2 ports, but this one is shut down. So it works very well. If you use regular spanning tree, you can literally just unplug the power plug from a switch, and everything will just refigure out where it's going. It takes about 10 seconds for that to happen. So if you work within your 5 nines thing, you can do that about 30 times a year. So if you need to upgrade the firmware or something like that, you can do that. There's also an alternate to spanning tree called rapid spanning tree. I think it's 802.1w, which gives you really, really fast failover. Basically, the way it works is that rather than actually blocking a port, it'll just shut down any non-broadcast frames on it. So you'll still maintain spanning tree sessions between all ports, even if they're shut down. So you can actually do that in less than 5 seconds. It usually averages around 3 to 4. So it gives you a lot more flexibility. With obviously connected to a Linux box, it gives you the advantage that when you unplug a switch, the Linux box will automatically figure out which one to go out. Linux right now, I believe, does not support rapid spanning tree, but you can use both rapid spanning tree and regular spanning tree on the same network. And a Linux system will just go and it'll do the spanning tree exchange. It'll see what's on the network and it'll just shut one of the ports down. If the other port becomes unavailable, then it will just start sending traffic to the other one. So this is all stuff you can tune. If you're really insane, you can make spanning tree send packets out every second for updates, and then set the dead time on it to 5 seconds, and it will still work. But it's worth bearing in mind that the lower the dead time is, the more impact small changes would have on it. So if you have to just move a cable, then you have to make sure you do it really quick. That's an example of setting up a bridge in Linux using ETH1 and ETH0 as ports. Pretty boring. But it lets you plug one box.
It works on the WRT too.
It does?
Yeah.
Excellent.
And everything.
Everything.
VLANs too.
Cool. So yeah, this is the simple way to get a Linux box with 2 NICs, plug it into a couple of switches, get some redundancy. So any questions at this point? Yes?
The recommendation of how powerful the machine can be?
Depends what you're doing with it. 10100 network, I would probably want a Pentium. The main consideration is the speed of your bus on the motherboard. So something that's running at 100 or 133 megahertz is probably a better choice than something that's running at 33. Until you start using gigabit Ethernet, anything greater than a Pentium 200 is probably fine. I think probably low-end Pentium 2 can easily handle 100 meg of traffic. Obviously, bridging, you can handle more traffic through a bridge than you can with a router. But you can still, if you're just doing basic routing, the Pentium 200 is still going to do pretty well. Once you start getting into more complex networking configurations, say if you're doing NAT on it, once you start NATing 100 meg of traffic, you start using a lot of memory and a lot of CPU just for that. So, it really depends upon the type of traffic that you have. Even on a 10100 network, you're probably not doing 10100 out to the internet. You've probably got like a couple of T1s, if that. So, or a cable or DSL or whatever else. So you're still limited at some point to a small pipe. So you really don't need anything too extravagant. Depending what else you're doing with the router, if you're going to run any routing protocols on it, if you're going to run anything like IPsec or any VPN stuff, that needs a little bit more horsepower. But in reality, unless you have a really complicated network, something pretty simple is going to cut it. Of course, the one thing to bear in mind with any router, if it's an old box, you want to make sure it's going to run solid. You want to make sure the power supply is good, make sure the memory's good, because as soon as you have a flaky router, people know about it. So you kind of have to make sure you're okay there. But you really don't need a whole lot of horsepower for any of this stuff. It's all pretty basic. Anything else before we move on? Nope. Okay. Okay. Everybody knows what IP is in terms of networking. It's what is referred to as a routed protocol. Protocols like IPX are not routed in that they all exist inside one network. So IP, you can actually route between separate Ethernet segments. And to do that, you use a router. So a router is essentially a IP switch. So you can think of a switch as being a Ethernet router. It will route Ethernet frames out of a port. A router will route IP packets out of an interface. So I like to differentiate my layer 2 and layer 3 stuff by saying layer 2 has ports, layer 3 has interfaces. So it may be the same thing physically, but it just makes more sense to do it that way. So you have an Ethernet port at layer 2 and an Ethernet interface at layer 3. And obviously then at layer 1 you actually have an Ethernet hole to plug stuff into. So a router will provide routing capabilities between physical separate Ethernet segments or VLANs within a network. So if you have a network and you chop it up into different little networks using VLANs, then you use the router to route between all of them. Within this, there's a routing table that basically it's like a little index to say, if I want to get to this box, send it out this interface. Want to go to this one, send it out this interface. Pretty basic stuff. Because it is a routed protocol, we can use a routing protocol to distribute the route information between multiple systems. The main two that are used on systems these days are OSPF, which stands for Open Shortest Path First, which is a protocol used inside a network. To talk between networks, you use a system called BGP. Anybody who has ever worked with an ISP or done anything more extravagant than cable modems will know that BGP is very, very complicated. It's one of those things that you go through a couple of weeks not understanding it, then it kind of clicks in your head how it all works. So BGP is something that is pretty complex to understand, and it's certainly, I mean, I wouldn't say it's outside the realms of a normal person's knowledge, but it's something that if you're going to use it, take the time to figure it out before you start messing with it, because once you start messing with BGP and you start having route flaps and all this kind of stuff, then you can really get yourself into some trouble. Like I said, OSPF used inside a network. Basically, if you have two routers, each with various routes on them, they will talk OSPF between the two of them and distribute all of the routes between them. So I don't have to go, if I have a network of 20 routers, I can add a route to one and all the rest just learn it from that. So it's really, really simple for setting up a network. The great thing about OSPF is that you can have multiple paths to one particular route. So if one router fails, it will just use an alternate path to get to that route. Now, compared to a protocol known as RIP that existed it still exists, but nobody uses it. RIP would actually be a protocol that would go out and basically every 30 seconds say, okay, what are the routes? What are the routes?